Very good morning, students. In the third unit of our FEA, we are going to see about two-dimensional elements. So, in the previous chapter, that is in Unit 2, we would have studied about that is one-dimensional element like a bar element or a truss element or beam element. So, in one-dimensional, we would have studied about a bar or a rod element and truss, then beams. So all these things. So here what you would have analyzed. So you have done first one is structural analysis. So in this displacement, the stress induced, all these things you would have found out this. So generally we will divide that into two different types. One is structural and another one is thermal. Right. So the temperature distribution on these elements, one-dimensional elements, can also be that is what you say. You would have analyzed. But in the unit 3, we are going to see about two-dimensional elements. So here, the two-dimensional elements, some of the examples for two-dimensional elements are, say, a circle, a triangle, or a square, or a rectangle, or even some, we can say, some semicircle or trapezium. Right? All these are the standard figures in two dimension. So when you consider the elements on among these one of these things, so there may be the variation in the results of the analysis. But generally, we go for a triangular element which suits better than the other elements, because see, all these can be again and again you can that is what you say, discretize in sense dividing the entire domain into subdomains. See, suppose for example if you have a square, so this square can be divided into several triangles. So like this we can divide. So suppose if you want to have still finer in size, the element would be, again it would be divided. So several triangles. Similarly, suppose if you take semicircle, so here this can also be divided into several triangles. So like this, all these elements can be further divided, and finally the least geometry, with the least geometry, that means that it has only three sides, and it is a complete element because it is closed, right? So this itself is enough. So that is why we are going for CST element. So what you called this is CST element, that is constant strain triangular element. So this CST element is the one which we are going to see in this third unit. So how we do the analysis, like there is finding the elemental matrices, then assemblage of those things, then global matrices, and substituting in the finite element equation. So all those steps, again it is here also it is followed, but the thing is here we are dealing with a two-dimensional element called a triangular element. So this is what. So what is this constant strain triangular element? See, this is a triangle, or so this is a triangle. See what we will have here. So we have three nodes. So node number say this is 1, this is node 2, and this is node 3. So since it's a two-dimensional element, and under the load, it it may subject to undergo two displacements, one on horizontal, another one is vertical. Okay, so this is how. So let us say this is the displacement as u1 and this one as u2. Or we can say v1, then u2 v2, then u3 v3. So all this u1, u2, u3 are all the horizontal nodal displacements. Under this v1, v2, v3 all are vertical nodal displacements. Okay, so this is how. See, when you consider this a triangle, it has three vertices, so obviously it will have the coordinates. So let these coordinates at node 1 may be x1 and y1, and here say this is x2, y2, and here this is x3, y3. So clearly the coordinates of the vertices 1, 2, 3 are the coordinates of the nodes. So at node 1 it has the coordinate x1, y1, right? So this is what you have to infer from this one. And at node 2 it is x2, y2. At node 3 it is x3, y3. Or even we can represent this like 1, 2 of 3 of like this. And here this u1, u2, u3 there is v1, v2, v3. So all these things are denoting the displacements. Okay. So now coming to the stiffness matrices. See, first thing is what we have to, what we need to find here is the stiffness matrix. See, as per the definition, right? Generally, this stiffness matrix is equal to B transpose into D into B into volume, so that we can write like area into its thickness or the length. Okay, so here what is this B is called? This B is called as strain displacement matrix. And what about this D is denoting? Is stress strain relationship matrix, as like what we have seen in the previous chapter. Okay, so here we don't have any problem. Actually we will have this B as 1 by 2a. So I am just writing the formula for B. 1 by 2a and it would be a 3 by 6 matrix where we will have see beta 1 0, beta 2 0, beta 3 0, 0 gamma 1, 0 gamma 2, 0 gamma 3, and this gamma 1 beta 1, gamma 2 beta 2, gamma 3 beta 3. Okay, so this is the formula for this one. I will tell you what is this area and how you will find out this one. See, area, that is A, is equal to 1 by 2 of the determinant. So what are the coordinates? So 1 x1 y1, 1 x2 y2, and 1 x3 y3. So from which you can find out this area. And what about this beta and gamma? So that we have to know. This beta 1 is nothing but y2 minus y3. Beta 2 is y3 minus y1. You know the coordinates x1, y1, x2, y2, x3, y3. So from which we can calculate these values. So this becomes y1 minus y2. And how this gamma 1 and gamma 2, gamma 3 will be calculated from the x coordinates. See here, it is of order say 1, 2, 3, 2, 3, 1, 3, 1, 2. So this is how we can take in this order. So here just you reverse the order. So this is why I am saying for easy remembrance. So this will be x3 minus x2, x1 minus x3, and here x2 minus x1. So this is how we can find out this gamma. So once you find this area, beta values, gamma values, you can find out this one. So in the next video, we will see how we can find out the stress-strain relationship matrix. Okay, so here the stress-strain relationship matrix can be found in two ways, considering the problem as a plane stress problem or a plane strain problem. So that we will see in the next video. Thank you.